All right, this is going to be our walkthrough for the homework assignment titled Finding the Derivative at a Point. So anytime you're asked to find the slope of the tangent line or the slope of the function at a point, or to find the instantaneous rate of change of a function at a point, you just need to take the derivative and evaluate it at the given x value or the given point. So we'll just find our derivative here using the power rule. It'll be 10x plus 3, and then all we have to do is just find y prime at 2, which will be 10 times 2 plus 3, or 23. For our second one here, again, this is just going to be a power rule problem. So we'll find y prime. That'll be negative 15x to the negative 4. Or we could write this as negative 15 over x to the 4th. And then when we evaluate this at 3, we should end up getting negative 15 over 81, which of course we can divide both top and bottom by 3, which should be negative 5 over 27. For our third one here, we're going to have to use the quotient rule to find the derivative. Okay? So we'll write out the quotient rule. It's v du minus u dv all over v squared, where your function is u over v. So our derivative, y prime, ought to be 5x minus 1 times the derivative of x plus 2, which is just 1, and then minus our x plus 2 times the derivative of 5x minus 1, which is 5, all divided by 5x minus 1 squared. Now, if you want to, you can go through and you can simplify this, or you can just go right ahead and plug in the x value of 4 here. Doesn't really matter. I think I'll just plug in the x value of 4. So it looks like we have 5 times 4. In fact, I'm going to write this sign here. We're going to evaluate this at x equals 4. Remember that vertical line means evaluated at. So 5 times 4 is 20, minus 1 would be 19. And then we're going to subtract from that 4 plus 2, which is 6, times 5, which will be 30. And in our denominator, we're going to have 5 times 4, which is 20, minus 1, it's 19, 19 squared. So 19 minus 30 is negative 11, and 19 squared is 361. And that should be our final answer there for number 3. For our fourth one here, we've got x squared e to the x. So that's two functions, u and v, being multiplied together. So we'll have to use the product rule to find the derivative here, u dv plus v du. So we'll have y prime is x squared, our u, times our derivative of e to the x. Well, the derivative of e to the x is just e to the x. And then we'll add to that e to the x times the derivative of u, which is 2x. And then we can just go right in and we can solve this at x equals 3. So we'll say y prime at 3 should equal, well, 3 squared is 9. So 9e cubed plus 2 times 3 is 6, so 6e cubed. And 9e cubed plus 6e cubed ought to be 15e cubed. And again, you can simplify this first if you want to factor out the x e to the x first. That makes it easier for you to evaluate. That's fine. It doesn't really matter now in this case if we simplify our derivative because we're just evaluating it at a point. I don't need to see a simplified derivative. All right, for our next one here, again, we have a product of two functions. We have u times v. So we'll do u dv plus v du. Our y prime then should be u, 3x minus 1. And then the derivative of v, well, the derivative of a to the x is just a to the x times the natural log of a, which is 2 in this case. Right, so there's our u dv, and then plus our v, which is 2 to the x, times our du, the derivative of 3x minus 1, is just 3. And so we can go through here and we can just plug in our x equals 5 and get ourselves a final answer. So y prime of 5 ought to be, well, let's see here. We've got 3 times 5 is 15. 15 minus 1 will be 14. And then 2 to the 5th power ought to be 32. So we have 14 times 32 times the natural log of 2. And then we're going to add to that, this other term here is going to be 32 times 3. You can multiply all that out, or you can factor that out and say it's 32 times 14 ln 2 plus 3. That answer would be fine if you distribute the 32 through it all. That's fine as well. All right, for number 6 here, we've got a quotient of two functions again. So it's e to the x over ln x, that's u over v. So we'll use the quotient rule, v du minus u dv, all over v squared. So our derivative, y prime, ought to be the denominator, natural log of x, times the derivative of the numerator. The derivative of e to the x is just e to the x. And then minus our numerator, which is again e to the x, times the derivative of natural log, which we should know that rule, it's 1 over x, all divided by the natural log of x squared. And then we'll just need to plug in our x value that was given. So we're going to evaluate this when x equals e. Well, all of these terms that are the natural log of e, the natural log of e is just 1. So when I do right here, the natural log of e, that's 1, so I can just kind of ignore that. And this, the natural log of e, is also just 1. And if I square 1, well, that can be ignored as well. So really, all we're looking at here is these other few terms. We should end up with e to the power of e minus e to the power of e times 1 over e, so over e. And that is our final answer. For number 7, we once again have a product of two functions here. This is u times v. So we're going to do u dv plus v du. So y prime ought to be the sine of 3x times the derivative of the cosine of 2x. And we'll write that off to the side since it's a chain rule. It's cosine of, we'll call it w, where w is 2x. So we should get negative sine of w times 2. So that'll be the negative 2 sine 2x. And then we'll add to that our v, which is cosine 2x, times our derivative of u. Well, the derivative of u, that's going to be the sine of z, where z is equal to 3x. So that'll be cosine z times 3, or 3 cosine 3x. Now we want to evaluate this at pi. So we're looking for y prime at pi. Well, that's the sine of 3 pi times negative 2 sine 2 pi plus cosine 2 pi times 3 cosine 3 pi. First thing we should note is that the sine of 3 pi and the sine of 2 pi are both 0. So this whole first term is just going to go away. And then 2 pi is the same as, finding the cosine of 2 pi is the same as finding the cosine of 0. We should know the cosine of 0 is 1, the cosine of 2 pi is 1. So we've got 1 here, so that one's not even going to really matter. And then we've got our 3 times the cosine of 3 pi. Well, the cosine of 3 pi is just like taking the cosine of pi, and that's negative 1. So our final answer should just be negative 3. For number 8 here, we're looking at the natural log of x squared. So we've got two ways to take this derivative. One is we can just use the chain rule. But the other way, which I think I'll use this time, I think probably in the answer key I might have used the chain rule. But we can also just call this 2 natural log of x. And if we call that 2 natural log of x, then y prime is just 2 times the derivative of natural log of x, which is 1 over x. And if we want to evaluate this at 3, we just get 2/3. So fairly straightforward there. If you use the chain rule, right, if you called this natural log of u, where u is equal to x squared, you'd see that you just get 1 over u times 2x, which would be 2x over x squared, which is still 2 over x. Just a couple extra little steps there to get the same derivative, and then you'd get 2/3 again when you plugged in a 3. All right, for our next one here, we have log base 4 of a function, right? So this is y equals log base 4 of u, where u is x squared minus x minus 1. So we need to use the derivative rule for log base a of u, which says that dy dx should be 1 over u times the natural log of that base. And then we multiply it by the derivative of u, which will just be 2x minus 1. So this looks like 2x minus 1 over x squared minus x minus 1 times the natural log of 4. And if we want to evaluate this at x equals 4, then at x equals 4, dy dx should be 2 times 4 is 8, and 8 minus 1 is 7. And then our denominator, we've got 4 squared is 16, and then 16 minus 4 is 12, and then 12 minus 1 is 11. So we have 11 natural log of 4. All right, for x squared plus 1 over the cosine of x, we'll note that this is u divided by v, right? This is u divided by v. So we're going to use v du minus u dv all over v squared, right? We'll use our quotient rule. So y prime ought to be our denominator, cosine x, times our derivative of x squared plus 1, which is 2x. And then minus the x squared plus 1 times the derivative of cosine of x. Well, the derivative of cosine is negative sine. So I will just change the sign of this and make that a positive sign, because it would be a negative sign. And then in our denominator, we just have cosine squared of x now. And if we're looking to evaluate this at pi, well, the cosine of pi is negative 1. And then 2 times pi is just 2 pi. And then in that second term, if we're looking for the sine of pi, well, the sine of pi is just 0. So I don't really need to worry about what the x squared plus 1 is, right? This is 0, and 0 times anything is going to give us 0. So we'll get rid of that. And then in our denominator, we have the cosine of pi, which is negative 1, squared. Well, that's just going to be 1. So our final answer is just what our numerator was, which is negative 2 pi. All right, halfway there. For our next one here, we've got the natural log of the sine of x squared. We're going to evaluate it at x equals root pi over 6. So this is y equals the natural log of a function, where that function is the sine of x squared. So we'll note that the sine of x squared is going to require us to use the chain rule also. This is u equals the sine of v, where v is equal to x squared. So we have 3 different pieces here to take derivatives of for the chain rule. Our first one, dy du, is going to be 1 over u. Our second one, du dv, is going to be cosine of v. And our last one, dv dx, is going to be 2x. So our final derivative here, dy dx, will be the 2x times the cosine of v. V is x squared, all divided by our function u, which was the sine of x squared. So that should be our derivative. And then we just need to go in and evaluate this at x equals the square root of pi over 6. So looks like that's going to give us 2 times the square root of pi over 6 to start with. And then we have the cosine of pi over 6. And then in the denominator, we're going to have the sine of pi over 6. And we should know what all those values are, right? The cosine of pi over 6 ought to be root 3 over 2. And the sine of pi over 6 ought to be 1/2. And so we can then we can simplify this down a little bit. If we've got the and that kind of looks bad there. It's root 3 over 2. I kind of made that look like the whole 3/2 was in the denominator, which it's not. So the 2 here and the 2 here ought to cancel out, right? And then we have this divided by 1/2 in our denominator, which is the same as multiplying by 2. So now we've got 2 root pi over 6 times root 3. Well, a square root times another square root, you can combine those together into one square root. So that'll be 2 root 3 pi over 6. And obviously 3 pi over 6 can simplify down to root pi over 2. So we have 2 times the square root of pi over 2 as our final answer here for that one. All right, here's our next one. We've got an inverse tangent function here. So we're looking at the inverse tangent of u, where u is 7x. So in order to find this derivative, we'll use the chain rule, right? We'll use the derivative of inverse tangent, which is 1 over 1 plus u squared. And then we'll multiply it by the derivative of u, which is just 7. So we end up with our dy dx equal to 7 over 1 plus 7x squared. And if we're going to evaluate this at x equals 2, that's just going to be 7 over 1 plus 14 squared, because 7 times 2 is 14. 14 squared is 196. So if we add 1 to that, we should get 197. 7 over 197. All right, for number 13 here, we've got a quotient of two functions. We're back to the quotient rule. So I'm going to write this out. This is u over v, and our quotient rule is v du minus u dv, all over v squared. So we'll start with v. For our y prime, it should be x squared, and then times the derivative of the inverse sine of 2x. Well, let's think about that. The inverse sine of 2x is a composition of functions. It's the inverse sine of w, where w is 2x. So we need to get 1 over root 1 minus w squared, which is the rule for inverse sine of w's derivative, and then times the 2 for the dw dx. So we're going to have a 2 here, and we're going to have it over root 1 minus our 2x squared. So that's the v du. Then we'll have minus u, which is inverse sine of 2x, times dv, which is just 2x. We'll divide it all by our denominator squared, which in this case is going to be x squared squared. We should know that x squared squared is x to the 4th. Then we want to evaluate this at x equals 1/4. So let's plug all of this in to our derivative and see if we can simplify it down. So if we plug in 1/4, we have 2 times 1/4 squared first, and 1/4 squared is 1/16. So 2 1/16 would be 2/16, or 1/8. So we have 1/8, and then that's divided by the square root of 1 minus 2x squared. So 2x, right, 2 times 1/4 is a half. And if we square 1/2, we should get 1/4. So this becomes the square root of 1 minus 1/4. Well, 1 minus 1/4 is 3/4. So this is the square root of 3/4. And then we can square root the denominator of that. That's the square root of 3 over 2. So our v du part ends up being 1/8 divided by root 3 over 2. And then we'll subtract from that our 2x. So that's going to be 2 times a fourth, or a half. And then the inverse sine of 2x, right? So the inverse sine of 1/2, and we'll evaluate that in a second. And then it's all going to be divided by 1/4 to the 4th power. And 4 to the 4th is 256, so that's 1/256. So let's kind of section this off a little here. Now we're going to say that's equal to, let's see if we can simplify that down a bit. The 1/8 divided by the √3/2, we can flip that √3/2 and multiply, and we should see that we get 1/4√3 if we do that. Right? Because the 2 and the 8 will cancel into a 1/4, and that √3 stays in the denominator. The inverse sine of 1/2, we know that when we take the inverse sine of something, it always has to come out to be something between -pi/2 and pi/2. And since this is a positive angle, it's going to be between 0 and pi/2. So we think about what angle between 0 and pi/2, when we take its sine, gives us half. Well, that'd be pi/6. And so we have 1/2 of pi/6. So that's going to be pi/12. So minus pi/12 here. And then we're dividing by 1/256. So really, we're just multiplying this by 256. And if you want to go in there and, distribute that 256 through, you can. I don't really necessarily need you to do that. 256 divided by 4 ought to just be 64, so you get 64/√3. And then, we can write it out. We get 64/√3, and then the 256 pi/12. Well, 256 can be divided by 4. It becomes, again, 64. And so we'd end up with that equals 60, not equals, but we'd have a minus there, our 64/3 if we reduced that fraction down. So that'd be fine, or you can just leave it as it was. If you want to put those together with the common denominator, you could do that. It doesn't really matter. All right, here we've got the inverse secant of √x. So if we're doing the inverse secant of √x, that's the inverse secant of u, where u is √x. So our derivative should be 1 over absolute value of u times the square root of u squared minus 1. And then we should multiply that by the derivative of √x, 1/2√x, right? That's our chain rule. So as we simplify this down, we should get dy dx is equal to 1 over the, we have a 2 out in the front, right? And then we have this 2 right here. Then we have the absolute value of u. Well, square roots are always positive or 0, so I don't need to worry about the absolute value. That's just √x. And then I've got this other √x, right, from the piece right here. And then I've got a root of u squared. Well, √x squared is just going to be x, so it's x minus 1. And so we could simplify this down so that it just looks like 1/2x √x minus 1. And so if we take 1/2x √x minus 1 and evaluate it at x equals 2, we should get 1/4 times the square root of 1, which should just be 1/4. All right, here we go. Number 15, we have the natural log of a function. So we'll use the chain rule to take the derivative. It's natural log u, where u is e to the x plus 1. So when we take our derivative here, we should get 1/u times the derivative of u, which is e to the x plus 1, right? E to the x's derivative is e to the x. The derivative of x is just 1, and the plus 1 is a constant, so it goes away. So our dy dx is just equal to e to the x plus 1 divided by e to the x plus 1. And if we're asked to evaluate this when x equals 0, so dy dx evaluated at x equals 0, well, e to the 0, we'll write it out, e to the 0 plus 1 over e to the 0 plus 0 plus 1 ends up being 1 plus 1 over 1 plus 1, which is just 1. All right, for our last few here, we're going to have to use implicit differentiation. And we'll note that now we're given x and y values. So that means that our derivatives are going to have x's and y's in them at the end. So our derivative of xy using the product rule is x times the derivative of y with respect to x plus y times the derivative of x, which is just 1. Then we get plus 3y squared dy dx. For the y cubed, we get 2x for the x squared, and for the y squared, we get 2y dy dx. The plus 13 falls off because the derivative of a constant is 0. We'll get all of our dy dx's to one side. I'm going to bring them to the left-hand side, and as I do that, I'm just going to factor out the dy dx. So I'll have a 3y squared plus a 2y when I bring the minus 2y over. And then on the, we also have an x. Let's not forget the x. We also have this x term here, so plus x. And then on the other side, we're going to have the 2x minus this y that we're going to bring over, which should give us dy dx is equal to 2x minus y over 3y squared plus 2y plus x. And now we'll just evaluate this at the point 1, 2. So if x is 1, we're going to have 2 times 1, and then minus the y of 2. Right? Looks like we're going to have a 0 in our numerator there. Let's just make sure our denominator is not also 0, because if it's not, then the whole thing is just 0. So we have 3 times 2 squared plus 2 times 2 plus 1, which is clearly not 0. So this just evaluates out to be 0 since the numerator is 0. All right, for this next one, we start off with the sine of xy. Well, in order to find that derivative, that's a chain rule derivative. So we take the derivative of the sine to get the cosine of xy, but then we have to multiply that by the derivative of xy. Well, the derivative of xy, we'll use the product rule for. It's x times the derivative of y with respect to x plus y times the derivative of x, which is just 1. Then we end up with plus 2x for our x squared and minus dy dx for our minus y. And then on the right-hand side, I think I'm going to just say that we have a negative 1/2 times xy, and I can put that constant out in front, and then multiply that by the derivative of xy, which we just did. It's x dy dx plus y. And then the plus 4 is going to cancel out and become 0. So we can go about this in 2 ways. One, we can just solve for dy dx and then plug in the point. Or we could plug in the point right now and then solve for dy dx. Now, I normally just solve for dy dx because often the problems will ask you find dy dx and then evaluate it at the point. So our first step in doing that will be to distribute this cosine xy to everything. So we'll have x cosine xy dy dx plus y cosine xy plus 2x minus dy dx equals negative 1/2 x dy dx minus 1/2 y. Then our goal will be to get everything on one side with the dy dx and everything else onto the other side. So I think I'll move my dy dx terms to the right-hand side, I guess. So as I do that on the left-hand side, I'm still going to have my y cosine xy, and I'm still going to have my plus 2x, and this minus 1/2 y is going to come over as a plus 1/2 y. And then on the other side, we'll have all the terms are going to have that dy dx, so we can factor the dy dx out of it. We'll have a minus 1/2 x. We'll have a plus 1 from this term. And then from our x cosine xy, over here we'll have a minus x cosine xy. And so our final derivative should be dy dx is equal to y cosine xy plus 2x plus 1/2 y, all divided by the negative 1/2 x plus 1 minus x cosine of xy. And if we evaluate that at the point 2 comma pi, well, that's going to give us y. So that's going to give us a pi here at the beginning. And then it's going to give us the cosine of 2 pi. Well, the cosine of 2 pi, we should know, is the same as the cosine of 0. So that's just 1. Right? So we just have the pi there. And then we're going to have pi plus our 2x, right? So 2x is just going to be 4. So we're going to have pi plus 4. And then we're going to have plus 1/2 of y, which would be plus pi over 2. And then in our denominator, we're going to have negative 1/2 of x, which is going to be a negative 1. Then we'll have that plus 1. And then we will have minus our x value, so minus 2, times the cosine of 2 pi. Well, we know that we just found, that's just 1, so we just have the minus 2 there. And now, looks like we end up with pi plus pi over 2. Well, that'd be 3 pi over 2. So it looks like we're going to have a 3 pi over 2 plus a 4 divided by negative 2, which should be negative 3 pi over 4 minus 2. And that should be our final answer there for number 17. So just a couple more here to go. This one, again, we're going to use the product rule. In fact, we're going to use the product rule 3 times. We're going to start with x squared times the derivative of y with respect to x. And then we'll add to that the derivative of x squared, which is 2x, times y. So that's this first term. Our second term should be x times the derivative of y squared, which is going to be a 2y dy dx, plus, then we need the derivative of the x, which is just 1, times the y squared. And then on the right-hand side, the 2xy will be 2x times the derivative of y with respect to x, plus the derivative of 2x, which is 2, times the y. So now we just need to gather all the dy dx's. This time I think we'll do it to the left-hand side here. So looks like we're going to have a dy dx times the x squared plus the 2xy from the first dy dx terms, and then minus a 2x as we bring this one over. And then we'll have a 2y, this on the right-hand side, minus the 2xy that we need to bring over, and minus the y squared that we need to bring over. So that we get dy dx is equal to 2y minus 2xy minus y squared, all divided by x squared plus 2xy minus 2x. And again, you can always bring them to the opposite sides and you'll just have all the signs flipped. But when you evaluate at the point 1, 1, you'll still get the exact same final value. So when we plug in our 1's, looks like we have 2 times 1, which is 2, minus 2 times 1 times 1, which is minus 2, minus 1 squared should be minus 1. And then in the denominator, we've got 1 plus 2 minus 2. So it looks like we end up with negative 1 over 1, or just negative 1. All right, second to last one here, we're going to use the product rule here on x sine y. So that should be x times the derivative of sine y, which is cosine y, dy dx. Then we'll add to that the derivative of x, which is 1 times sine y, right? So that's just the product rule. Then we'll take the derivative of tangent y, which should be a plus secant squared y dy dx. And then our derivative of x squared, which ought to just be 2x. All the dy dx's are already on the left-hand side, so we'll just factor that out. We'll have x cosine y plus secant squared y is equal to 2x minus the sine y that needs to be brought to the right-hand side. And then we'll just divide. Dy dx should be 2x minus sine of y divided by x cosine y plus secant squared y. And we'll evaluate that at the point root 2 comma 4. Sorry, not 4, pi over 4. So as we plug those in, the 2x should just be a 2 root 2. And the sine of y, well, the sine of pi over 4 is root 2 over 2, so that'll be minus root 2 over 2. And then in our denominator, we're going to have our x value, root 2, times the cosine of pi over 4, which is root 2 over 2. And then we'll add to that the secant squared of pi over 4. Well, the secant of pi over 4 is just root 2, so if we square that, it should be 2. And you should be able to find the secant of y. If you're not sure about that, remember that's 1 over cosine squared y. Right, so that's just 1 over the cosine of pi over 4 squared. Well, the cosine of pi over 4 is root 2 over 2. So 1 over root 2 over 2 squared, which is 1 over 2/4. If you take the reciprocal of 2/4, that's 4 over 2, which is just 2. So if you don't just remember that the secant of pi over 4 is root 2, you can do this process with the sines and the cosines that you probably know a little bit better. But anyway, now we should just simplify this down. So 2 root 2 minus root 2 over 2. Well, that's 2 root 2's minus a half of root 2. So that seems like that would just be 3 root 2 over 2. Right? If we got a common denominator, we'd see it's 4 root 2 minus 1 root 2 all over 2. And then in the denominator, we've got root 2 over 2 times root 2 over 2. Well, root 2 over 2 times root 2 over 2 is 2. And then the 2 over the 2 becomes just a 1. So that whole term is just 1 plus 2 makes 3. And the 3's will now cancel, and we just end up with our final answer of root 2 over 2. All right, for our last one here, we've got to use the quotient rule first to find the derivative of x plus y over x minus y. Then we'll use the product rule for the x squared, y squared. So our quotient rule, v, denominator, times derivative of u, which is 1 plus dy dx, right, if we're doing that with respect to x. So we have x minus y times 1 plus dy dx, minus our u, which is x plus y, times the derivative of x minus y, which will be 1 minus dy dx. And then that's all going to be divided by the x minus y squared. And then on the right-hand side, we're going to have the derivative of x squared, y squared. So that's going to be x squared times the derivative of y squared, which is 2y dy dx, plus the derivative of x squared, which is 2x, times y squared. And then the minus 41 just goes away because the derivative of a constant is 0. So now this might be an instance in which we don't want to distribute all of this out and solve for dy dx initially. If you do, that's fine. And I guess we can. But we might just want to plug in your x equals 2 and your y equals 3 right off the bat. Because if you do that, you can see that if x is 2 and y is 3, then this becomes 2 minus 3 squared. Well, that's negative 1 squared, which is just 1, right? So if I start doing this, I don't really have to worry about this term because that term is just a 1. And so if we go through then and we try and plug in our our 2 for x and our 3 for y, we're going to end up with 2 minus 3, which is negative 1. And then we're going to have 1 plus dy dx right there. And then we're going to have minus a 2 plus 3, which is just going to be 5 times a 1 minus dy dx. And on the other hand, on the other side, when we plug in our 2x squared y here, we're going to have 2 times 2 squared. Well, 2 times 2 squared is 8, and 8 times that 3 is going to be 24. So we'll have 24 dy dx over here. And then plus our 2xy squared. Well, y squared is 9, and 4 times 9 is 36. And so now we can just distribute this negative 1 and distribute this 5, and we should be able to fairly quickly solve for dy dx. So that's going to give us negative 1 minus dy dx, and then minus 5, and then plus 5 dy dx is equal to 24 dy dx plus 36. And so now as we go through and try to simplify this down, well, negative 1 minus 5 is negative 6. And if I add negative 6 to the other side, that's going to give me a 42 over here, right, the 36. And on this side, I'm going to have a negative 1 dy dx plus a 5 dy dx is 4 dy dx. And if I subtract the 24, that'll be negative 20 dy dx. And so we can then solve for dy dx and get, negative 42 20ths, which is just negative 21 over 10. And if you go through the process of solving for dy dx and then plugging in the 2, 3, you're going to get the exact same answer. But I think in this instance, where it's a fairly complicated derivative, you don't really need to do that. You can just go ahead and plug it in right away, unless the question asks you to find dy dx explicitly, in which case then you, of course, need to find dy dx. And I think in the answer key that I've got posted online, I think I found dy dx and then evaluated it, and you see that we'll come up with the same answer here. So either way you choose to do it is just fine. And that is it for our walkthrough of the homework assignment for finding the derivative at a point.